All right, let's get right into it. Today, we're going to pull back the curtain on some of the most important but totally overlooked structures in all of science. We're talking about the hidden architects of modern medicine.
Okay, so let me start by asking you a question. Think about this. What in the world do mothballs, some of our most powerful cancer drugs, and the actual chemical heart of morphine have in common? I mean, they sound completely unrelated, don't they?
Well, believe it or not, they all share the exact same molecular foundation. They're all built from something called polynuclear aromatic hydrocarbons. And yeah, I know that's a mouthful, but these are the unsung heroes we're going to be talking about today.
So let's get to know these molecular architects, shall we? You can think of them as these master builders, working behind the scenes, creating this incredible range of stuff that literally shapes our modern world.
So what are these things, these PAHs? Well, to put it simply, they're just organic compounds made up of a bunch of benzene rings. Those are a common type of carbon ring, all fused together. It's kind of like they're sharing walls, like rooms in a house. And it's from these super simple-looking frameworks that both nature and us chemists have built just an amazing number of useful things.
First up, we've got to talk about the most famous, or maybe infamous member of this family, naphthalene. And I know what you're thinking, mothballs, right? But trust me, there is so much more to this molecule than just protecting your sweaters.
And here it is. This is naphthalene, C10H8. It's the simplest PAH you can get. It's literally just two of those benzene rings stuck together, sharing one side. It's so clean, so elegant, and as you'll see, an incredibly versatile little blueprint.
Okay, now this is where it gets really interesting. Look at this diversity. Yeah, of course, we've got mothballs and fumigants. We all know that smell. But that exact same molecule is also used to make plastics softer, to create these really vivid dyes for clothes, and this is the amazing part, it's the starting material for some super important drugs, like the beta blocker propranolol. The stuff used for high blood pressure? Wild, right?
All right, let's level up. We're going to add one more ring to the mix. It's time to meet two molecular siblings. I'm talking about the three ring powerhouses, anthracene and phanthine. So here's the deal with these two. They're what chemists call isomers. That's just a fancy word meaning they have the exact same formula, C14H10, but a totally different shape. See how anthracene is just three rings in a perfectly straight line? But then you look at phanthine and it's got this kink, this angle to it. And that one tiny little difference in shape, it changes everything. It makes phanthine way more stable, and it unlocks a whole new universe of uses.
So let's start with the straight one, anthracene. That linear shape is perfect for making dyes, like the really famous red one called alizarin. But it also has this cool superpower. It scintillates, which basically means it flashes a little light whenever it gets hit by radiation. Super useful for detectors. And get this, some of its derivatives are even used as anti-cancer drugs. But this is where the story gets really, really good. That little bend in its brother, phanthine, that angle, turns out it's the structural heart of some of the most powerful medicines that nature has ever created. I mean, just look at this. That angular shape, that's the key. That specific structure is the literal backbone for powerful alkaloids like morphine and codeine. And if that's not enough, it's also the basic blueprint for all steroids. We're talking hormones, the whole shebang. So think about it. From a simple molecule you can find in coal tar, you get the foundation for our body's own chemical messengers and our strongest painkillers. Just incredible. And we're not done unlocking its secrets. Not even close. In fact, some really recent research on a plant from Brazil has found a derivative of phenanthrene that could be a brand new weapon in the fight against cancer.
So what does that mean?
Well, it comes down to this number, 2.59 micromolar. Now that's just a scientific measurement of potency. It's called the IC50 value. All you really need to know is that with this kind of measurement, the lower the number, the more powerful the compound is. And 2.59 is a very low number. It means this stuff is incredibly effective at killing melanoma cells, which makes it a super promising lead for brand new cancer treatments.
Okay, let's switch things up a bit. Our next group of architects are a little different. They don't have those fused rings we've been looking at, but they're still part of this powerful family. Let's talk about methane's famous offspring. And the way these are built is just so cool and simple. You start with the most basic building block of all, methane. That's just one carbon and 4 hydrogens. Then, you just swap out 2 of those hydrogens for these bigger rings, called phenyl groups, and boom, you've got diphenylmethane. Swap out a 3rd hydrogen and you get triphenylmethane. It's like playing with molecular Legos, Building up something complex from the simplest piece imaginable.
So let's look at the first one, diphenylmethane. I can almost guarantee you've got some of its legacy in your house right now. Why? Because it's the structural backbone for a ton of antihistamines, like the stuff in Benadryl that you take for allergies. And outside of the pharmacy, it actually has a nice smell, so it's used to make the scent in perfumes and soaps last longer.
Okay, now for its bigger sibling, Tryphenylmethane. This one's story isn't really about medicine or smells, it's all about color. And I love this quote because it says it all. Tryphenylmethane is the parent of an entire universe of color.
And it's so true. That three-ring structure is the basis for these super intense dyes, like crystal violet and malachite green. And they're not just for dyeing your clothes, they're actually vital tools for scientists. You'll find them used as pH indicators in labs. You know, the stuff that changes color to tell you if something is an acid or a base. And they're used to stain cells so biologists can actually see what's going on under a microscope.
So let's wrap this up. It's time to take a step back and just appreciate the absolutely incredible legacy of these molecular architects. And this chart really brings it all home, doesn't it? You've got naphthalene with its 2 rings, then the 3-ring isomers, phenanthrene and anthracene, and of course, those methane derivatives. And you can see how each unique shape, each little tweak in the structure leads to a totally different job. We're talking dyes, plastics, antihistamines, and even the core of morphine, all from these simple building blocks.
And that right there is the main takeaway. It's just mind-blowing when you think about it. These things often start out as just black sludge from coal tar or hidden in the roots of a plant. But then, through some clever chemistry or just the genius of nature, these simple carbon frameworks become the blueprints for incredible innovation. Life-saving drugs, essential materials, you name it.
Which really just leaves you with one final question, doesn't it? If these pretty simple-looking molecules gave us all of this, what other incredible blueprints are still hiding out there in nature, just waiting for someone to discover them?